I'm working on a circuit and some other work right now that measures inductance using a function generator, an integrated circuit, and a couple RL and RC differentiators and integrators. That work might make it into a future video, but in the course of doing that work, I began wondering about other simpler methods to measure inductance. Looking around a bit led to the Maxwell bridge circuit, which is an AC variant of the simpler Wheatstone bridge circuit. Working out the math and formulating some other thoughts on bridge circuits in general resulted in this video. In this episode, we'll look at some theory and then wire up a demo on the bench. So, let's get started. What's a bridge circuit? A bridge circuit is really nothing more than a circuit with two branches that are connected by a third, or bridging, branch. Bridges are a general approach for making measurements that are not based on any calibrated meter. Rather, you use the meter to obtain a null, or a balance between the two branches, and then you calculate the measurement based on other circuit elements that are known. And you can use this approach to measure resistance, inductance, capacitance, and impedance in general. Many people are familiar with the Wheatstone bridge, and so that's what we'll begin discussing here. The Wheatstone bridge is a way of making a measurement of an unknown resistor, in this case R4, based on a knowledge of three other resistive elements, R1, 2, and 3. Generally, one of these resistors is variable, so a potentiometer, and you circulate DC through this bridge and adjust R1 until there is no potential difference between these two nodes in the circuit. That is to say, this will be null, it will read 0. And from this condition, and knowing R1, 2, and 3, you can then calculate R4. Instead of making the calculation for R4 in that circuit, let's make a calculation for a circuit that's a little bit more general, and then we'll simplify that circuit at the end, at the last step, to get to the condition for the balance of the Wheatstone bridge. So first of all, we're going to consider the same circuit topology. This is exactly what I had drawn before, but instead of having four resistors, I'm going to represent four impedances, Z1, Z2, Z3, and Z4. And instead of applying a DC across the two nodes of the circuit, I'm going to feed it with an alternating current of a known frequency. So the impedances are nothing more than a function of the resistance and the reactive elements, which might be an inductive reactance or a capacitive reactance, or a combination of the two in general. And so we set the circuit up like this. So flowing through this branch of the circuit, we've got current I1. Flowing down here through Z2, we've got current I2. We have I4 flowing through Z4, and we have I3 flowing through Z3. We have nodes B and D here, and a galvanometer or a voltmeter measuring the potential difference between B and D. Flowing through that voltmeter is current IM, and it'll come up later that this meter is assumed to have a resistance R sub M. So recall that I said this is a null measurement, that we're interested in the case when these two branches of the circuit are balanced. There's no potential difference between B and D, which means that IM has to vanish. IM has to be 0. So let's apply Kirchhoff's current law to this circuit. And what Kirchhoff's law is a statement that the current flowing into a node, in this case node D, it has to be equal to the net outflows of current from that node. So what that means is, in this case, flowing into node D, we have I4, and there's only two choices the current can make when it gets to node D. It can either turn left and go towards the meter, or it can continue going and go towards node C through this impedance Z3. So we have I4 equals IM plus I3. And that is the first of our two node equations. Then we apply the same rationale to what's going on at node B. So we have I1, But now we have IM emerging from the meter and converging on this node. So we have I1 plus IM has to equal I2. And that's our second equation. But we supposed that IM is 0. So this is a very simple result that we have I1 equals I2 and I3 equals I4. What that means is when the circuit is in balance, the current in this part of the circuit is equal to the current in this part of the circuit, and the same for the left-hand side. All right, what does that get us? Well, that doesn't really get us too much until we look at Kirchhoff's voltage law. And let's just go back here and look at the circuit again. So Kirchhoff's voltage law, sometimes called the loop law, or the loop equations, states that the sum of the potential differences between elements in a loop has to add up to 0. All right. So for the first equation, we're going to do this loop here, and then we're going to do this loop down here. So the first equation is going to be the potential difference across this resistive element, this complex element, the Z1, is going to be I1 Z1, just applying Ohm's law to that. All right. And then there's going to be minus IM, because we're going, the sense of the loop is opposite to the current flow in this direction. So we have I1 Z1 minus IM RM. Ohm's law applied to the voltmeter. And then we're still going counter to the flow of current, so this is going to be minus I4 Z4. And all of those things have to add up to be 0. So that's our first KVL equation here. And then to do the same thing, but for the bottom loop now, we're going to have I2 Z2, voltage drop across this element, minus I3 Z3, but now we're going back across these two nodes in the positive sense, so this is going to be plus IM RM, has to be equal to 0. Okay, so that's that equation there. But again, we know that IM is equal to 0 when we have balance. So that just simplifies these equations to I1 Z1 equal I4 Z4, and I2 Z2 is equal to I3 Z3. Well, now we have two equations, one from the current law and one from the voltage law, and we can begin to combine those equations and do some algebra to find the unknown Z4. So dividing our two voltage equations by one another, we have I1 Z1 over I2 Z2 is equal to I4 Z4 over I3 Z3. But above, when we did KCL, we showed that I1 and I2 are the same, and I3 and I4 are the same. Okay? So what that means is now that these currents divide out of this equation, and what we're left with is the very simple condition that Z4 is equal to Z1 Z3 over Z2. So whatever the Z4 is, if we can calculate or measure Z1, Z2, and Z3, then we can compute Z4. Okay. Now, what does that get us? Well, in the case of the Wheatstone bridge, those Z's are just simply R's. So we have that an unknown R4 is just the product of R1 and R3 divided by R2. And it's very simple to work out. And, in the old days, or even today, you often, you have resistors that are known where you can measure them with your DMM. And so it's very easy to calculate this R4. No one in their right mind would actually use the Wheatstone bridge today to infer an unknown resistor on a workbench. You just grab your DMM. But in the old days, this was where, this was a way to make very sensitive measurements of changes in resistance. And in fact, this is actually still used today in some applications that we'll talk a little bit about a little bit later in the video. Okay. So the idea of bridge-based measurements is useful in a whole number of different scenarios. And in fact, you'll be probably familiar with one of those scenarios if you like old-time radios or old-time test equipment, because the bridge circuit is the basis for vacuum tube voltmeters. So here I've redrawn a vacuum tube voltmeter circuit in a way that looks a lot like the Wheatstone bridge. But instead of resistors on these two branches of the circuit, I've got triode vacuum tubes. Okay, so let's think about how this works. The current going through this vacuum tube that is flowing from this cathode to this plate is determined solely, it's determined solely by this B+, the potential on the plate, and the value of this resistor R4. There's no potential on this grid. It's grounded. It's isolated from ground by a resistor here, but there's no potential on it. So the current flowing through this bridge of the circuit, or this branch of the circuit, is a function of R4 and B+. Well, if we don't have any voltage, any signal on the grid of this vacuum tube, current flowing through this branch of the circuit is again determined by B+ and the value of R3. Never mind about R1 and R2 for a moment, just pretend those aren't there. Well, if this is the case, that R3 and R4 are equal to 0, then the same amount of current is flowing through these two vacuum tubes, the same voltage is dropped across these two resistors, and there's no potential difference between this node and this node. So this V should equal 0. There's no current flowing between these two nodes because they're at the same potential. And the meter that you see on the front of your VTM will read 0. So this bridge is in balance. R1 and R2 are potentiometers that are usually small in value, and they're adjusted so that you have this 0. R1 is usually it's called the zero adjust, and R2 is a calibration control. And these are meant to adjust just very small changes that take place over the lifetime of these tubes that affect the current flow, the properties of the tubes themselves. All right, so this tube is this VTVM is in balance when there's no voltage applied. If I apply a voltage now to this grid, and here I've written a resistor through here is 10 mega ohms, but in general this is a voltage divider network that's either 10 mega ohms or 25 mega ohms or whatever your particular VTVM input impedance is. You have a positive voltage showing up on the grid here. Well, what does that do? If I have a positive voltage here adding to the B+ on the plate, I'm going to attract more and more electrons off of this cathode. So the current increase, you'll see a current increase in the current flowing from the cathode to the plate. So there'll be an increase in current flowing through this branch of the bridge, and because of Ohm's law, increased current flowing through this fixed resistor will result in a higher voltage drop across this resistor. So this point will no longer be at the same potential as this point. There'll be a net current flowing through this meter right here, and you'll have a meter deflection. And that's how we measure voltages on a VTVM. So the VTVM is based on a bridge circuit, and it reads values when the bridge is out of balance. All right, so that's one application of a bridge circuit. You have to go back a few decades for that to be relevant. And oh, by the way, a more in-depth description of this circuit and other tube-based bridge circuits and VTVMs can be found by looking at Ryder's book on vacuum tube voltmeters. In the edition I have, it's in chapter 3, but it's just it's a really good book that goes into just the right amount of depth to understand all the different variations of bridge circuits and VTVMs. All right, well, going back even further than the VTVM, there is another application that I want to go through here just a bit. Let me zoom out a little bit here. That was actually developed by James Clerk Maxwell himself and was devised about the same time by Wien. And so this is now known as the Maxwell-Wien bridge. This is a bridge that enables one to measure unknown inductances. So we take this inductive element L2 to be unknown in the Maxwell-Wien bridge. And we calculate that based on obtaining a null between these two nodes and knowing what these three resistors are and this capacitive element. So, we went through some tedious algebra based on the Kirchhoff loop and node laws before to get this condition for balance. Here I've written it a bit differently. I've swapped these two around so that I've got Z2, because that's our unknown, is equal to Z1, Z3 over Z4. And what do we have to do now to calculate this unknown L? Well, we have to come up with expressions for the impedances of this branch of the circuit and this branch of the circuit. The impedance for this branch is just R1, and the impedance for this branch is just R3. So in this case, these two elements are in series, so Z2 is just going to be R2 plus J, where J is the square root of -1, omega, where omega is the angular frequency that I'm applying to this bridge, which is just 2 pi f, the usual frequency, the cyclic frequency, times L, the unknown. This branch might seem a little bit less benign, but it's not. We know how to combine resistors in parallel. That's just the product of the sum. Only here we're trying to combine a resistance and a capacitive reactance. And so those combine in exactly the same way. So this is going to be R4 times X sub C over R4 plus X sub C. X sub C is 1 over J omega times C. And so you can work all that out, and you will find out that Z4 is just R4 over 1 plus J omega RC. All right. Well, we can now go back to our balance condition here. And there's just a little bit of algebra that has to be done. And it involves combining the real, equating the real and imaginary parts of the balance equation. When you do that, you find, without too much trouble, that L is equal to R1, R3 times C4. So that's a very simple expression. If you know R1 and you know R3 and you know the capacitor, then you can compute the inductance of that circuit. So the big question is, how does this work in practice? Can I just throw this together on the bench and measure unknown inductances? Well, let's see if we can demonstrate it. All right, I've done this in a frankly completely unsatisfactory way. I've put it on a breadboard, and you'll remember that underneath the holes in these sorts of breadboards are metallic strips, and those strips themselves have capacitance between one another and inductances as well. So this is only meant to be a quick and dirty demonstration. So I've wired up a bridge circuit here, and I've picked some values of my two fixed resistors, and I've picked those to be 220 ohms and 3 kiloohms, because those were what were in arm's reach. I have a little potentiometer here, which is a 10K potentiometer that I'm going to adjust. And I have this rather large, physically large capacitor, which is 1/4 of a microfarad in value. And I've set up a function generator to produce a sine wave at 10 kilohertz. And so what I'm going to do is I'm going to adjust this potentiometer backwards and forwards, and I'm going to look for a null, and then I will take the potentiometer out of the circuit, measure what resistance I stopped at, and then use those values to compute the value of L. Let me just stop this for a moment here and use a bridge circuit to diagnose the bridge circuit. I'm going to use a vacuum tube voltmeter because the analog swing of the meter is really nice for identifying nulls. And we'll be right back. Here we are. So I've had my ICO VTVM warming up now for actually quite a while, several hours. And my Tektronix function generator that is putting out just right around 10 kilohertz. And so what I'm going to do now is I'm going to start adjusting the potentiometer on the bridge. And let me zero in a little bit more so we can see the meter better. Okay. So changing, so you can see we're approaching null. We went through the null, and now I'm going back the other way. And right about there is 0 volts. Okay. And so let's just see. Now let's take the potentiometer out of the circuit and see what we have. So we'll just do this in real time here. We'll zero in on this ohmmeter. All right. We'll take the pot out of the circuit and we'll measure what the resistance is. We get 195 ohms. What we're going to do now is we're going to, in real time, we're going to look at, we got, what, 195 ohms, and we multiply that by 220, right, because the formula is R1, R3, C4. Then we have 0.25 microfarads times, and the result is just about 10 times 10 to the minus 3, or 10 millihenries. And in fact, the inductor that I was using in this circuit, I know because I measured it independently on an LCR meter that I have, the DE5000, turned out to be 10 millihenries in reality. So you can see that just with a very unstressing job of throwing together a circuit on a breadboard and not actually measuring the resistors themselves with DMMs to get precise values or accurate values over the resistance, we can get in the ballpark, nicely in the ballpark, of what the actual value of this inductor was. All right, so it works, and that's kind of cool. Now, it's not quite as easily done in general for arbitrary values of inductors that you want to measure, because the ease of making this measurement depends on the Q of the inductor. And you might imagine that for very high or very low quality factors of the inductor, that null might be more difficult or less difficult to find. So this is not a panacea. The circuit has limitations, some of which can be dealt with by adding other elements to the circuit, which we won't go into here. There are many more classical variations on the Wheatstone bridge and the Maxwell bridge, and you can read about them in many textbooks on circuit theory, and I encourage you to do so if you're interested. In application, bridge circuits are sometimes found in transducer circuits of many different types, and one can measure antenna impedance with RF bridges. If you're interested in how to do that, I suggest that you look at the ARRL handbook or other similar publications. Well, I hope you found this interesting. If so, please give it a big thumbs up below, and as always, thank you for watching.